So, here we see a heart pattern, and this is a periodically repeating pattern. So, hearts are repeating in two directions, horizontal and vertical, and of course, as you know that any linear combination of these two vectors, if you select, it will be repeating in that direction also. So, if I see a heart at this vector at that direction, if I continue my journey, I will keep seeing identical heart in that direction. And not only that, I have to get a heart at the right location, I also have to get the heart in the correct orientation. So, suppose if I tilt the heart or turn it upside down or by 90° at the same location, matching the centroid, but rotating the heart, then the periodicity is lost. So, not only the position should be repeated, at that position the same object should come, and that same object should come in the same orientation. So, that is what is being seen in this heart pattern also, all hearts are identically oriented. Now, if we select, so we want to derive the lattice, this is a pattern, this is not a lattice, but a lattice belongs to this pattern, and to extract the lattice out of this pattern, I select a reference point, which I have called this R here, a reference point, which is the bottom of my heart. So, from the bottom of my heart, I go to another heart, and there also I select the bottom. So, identical feature of all the hearts has to be selected, not that if I select the bottom here and then if I select the centroid here and then I select this depression there. Depression of hearts is also very common these days. So, you may like to select that, but then you have to keep selecting the same identical points in all the hearts. So, here I am selecting bottom point, and if I select all the bottom points, then the lattice I get is here. So, I get a lattice. So, I remove the heart now, because I want to focus exactly on what is the repeat structure or what is the pattern which is repeating. So, that gives me this square grid of lattice points. So, I know that with each lattice point a heart is associated or something is associated. If you do not tell me heart, then also I will know that I am talking about some repeating pattern, where whatever is repeating has this repeat structure. So, the pattern was there and we extracted the lattice. From lattice, if I want to go back to the pattern, I have to know what is being repeated. So, that is an additional information, that information is not in the lattice. That is why for the pattern we require both lattice and the motif. So, let us look at some of these lattice and non-lattice translations we talked about yesterday, that in any given lattice, if I have a vector from one lattice point to another lattice point, like this vector A connecting two nearby lattice point, that is a lattice translation. So, this is a lattice translation, B is also a lattice translation. What about C? Lattice translation. D, keep saying yes or no, so that I know that you are with me. E? E, no. F? No. G? I am hearing yes as well as no. Yes. Why? Because vector wise, although I have not drawn it from lattice point to lattice point, but vector wise it will connect a lattice point to lattice point if I draw it from a lattice point. Only mistake this vector was doing, that it was not starting from a lattice point. But we know that vectors are translatable, vectors are not fixed, we are talking of free vectors. So, this vector also qualifies as a lattice vector, k is also a lattice vector, h is also a lattice vector. Good. Now, let us look at some examples of unit cells, which we looked at yesterday. So, again you tell me whether it is a unit cell and whether it is primitive or not primitive. So, is it a unit cell? Yeah. So, a primitive unit cell. So, let me write this as P. Still primitive. What about both are primitive? What about their size? Which is smaller? Area wise both are same. Who says so? Maths. And what is the theorem? Base into height I like better. Cross product is also right, but why go to the complication? So, parallelograms with same base and same height will always have same area. Triangles with same base and same height also have the same area. So, that simple theorem makes them having the same area. So, even sometimes one feels that there are infinitely many unit cells. There are infinitely many unit cells because there are so many different sizes of non primitive unit cell, but primitive unit cell is unique. No, primitive unit cell is also infinitely many. You can keep having the same volume in 3D or same area in 2D, but still have different primitive unit cell in terms of their shape. C primitive, D non primitive, E primitive, non primitive, not unit cell.
Should be a unit. No, not a unit cell.
What was the definition of unit cell?
Should tile the entire.
Will it tile or will it not tile?
It will.
Hmm?
It will.
It will tile?
Yes. It will overlap. No, sir. If we tile to tile, it should overlap.
Okay, left as an exercise, will not answer. F does not even have a straight edge.
Not a unit cell.
Will not tile?
It's a unit cell, primitive.
It will tile?
Yes.
Yes, primitive unit cell.
It's tiling. It is a primitive unit cell. Who said that it should have a straight edges? And that is what the artists use. And one of the greatest artists in this field, we will look at his artwork sometime, M.C. Escher, a Dutch artist, Dutch graphic artist. Very famous. In Google you will find thousands of things, and one of the things he was famous for was for creating periodic art. So, his art is having translational periodicity, one set of his art, not everything, one set of his, he means he wanted to play with all kinds of periodic, but his periodic, if you make it of squares or rectangles, who will buy your art? So, his figures were birds, lizards, devils, demons, angels, all sorts of figures which will be repeating and will be fitting exactly together. So, they are also unit cells, his figures are unit cells you can find, but with curved boundary. So, you can curve the boundary and still get the unit cell and you still have a repetition. G, this will not tile, because if I start repeating also, I find that I am leaving some gap. This, because I need this triangle also. to fill and this triangle is being left out. I can get this triangle by rotating this triangle or maybe reflecting in this edge, but that is not an allowed operation in the definition of unit cell. Unit cell should repeat by translational symmetry. Later on we will see there is another crystallographers do like this kind of thing also, that is start with a smaller region and allow to reflect or rotate to fill the space. That has a different jargon. I will share it with you, but we will look at it in detail later. That is called asymmetric unit. Asymmetric unit. So, asymmetric unit tiles by translation as well as rotation or reflection, that is allowed. If that was allowed, then this triangle will qualify in that definition, that I not only translate, I reflect it in this line, then I get this triangle, and then I translate. So, I get this triangle, and then I translate the green triangle. So, I get this triangle, then I will start filling the space. So, if rotation and reflection both are allowed, G will qualify, but then it will be a representative of asymmetric unit, not of unit cell. Unit cell, the limitation is that it has to fill by translation. In 3D, it was very nice to draw in 2D and we were playing with rhombuses or parallelograms or even some odd shapes we saw. But in 3 dimension, one of the standard unit cells is a parallelopiped unit cell. Parallelopiped you are familiar, 3 parallel, means 3 sets of parallelograms. So, each face is a parallelogram and there are pair of parallelograms which are parallel. So, the top and bottom, left and right and front and back. So, this is our parallelogram unit cell. Parallelogram, what is the beauty of parallelogram unit cell? It will always tile the space if it is repeated by translations equal to its edges. So, if if in this direction I translate by B, I get the next parallelogram. In the bottom direction, if I translate by minus C, I get that parallelogram. So, it will start filling the space. So, it is a unit cell. Parallelogram, parallelopiped are unit cells, and that is the standard unit cell usually used in crystallography. So, although by definition of unit cell and particularly in that example of 2D we just saw that variety of unit cells are possible even with curved boundaries and also in 3D also you can imagine. And yesterday we did see one non-parallelopiped unit cell. What was that? The Voronoi cell of the BCC. That was not parallelopiped, but that is a unit cell. So, 3D also it is possible to have shapes which are different from parallelopiped, but parallelopiped seems to be simple and standard. So, we try to use it most often than not. If some need is there, we do use. So, in solid state physics, when we require Brillouin zone or Wigner side cell, we deviate from parallelopipeds. Then this convention, you know, one of the edges is called A. So, that is the basis vector. So, now these are the basis vectors A, B and C. And for any given basis vector, either primitive basis vector. So, yesterday we saw that we have primitive basis vector, basis vectors, we had primitive and non-primitive, and if we make a parallelopiped out of a primitive basis vector, we get a primitive unit cell. Primitive unit cell. If we make a parallelopiped out of non-primitive vectors, non-primitive basis vector, we get non-primitive unit cell. And the standard convention is to call one of them A, B or C, or sometimes in more mathematically oriented discussion, sometimes it is better to use A1, A2 and A3, because then you can use index. So, for example, you can say I is equal to 1, 2, 3. So, that will represent all the 3 basis vectors, whereas in the case of A, B, C, you will have to write all 3 A, B, C. So, sometimes we will use both, we will use A, B, C also and we will use A1, A2, A3 also. A is for A1 is for A, A2 is for B and A3 is for C. And then the angles also are required, because edges alone will not define the shape of the parallelepiped. They can, these vectors can have different angles. So, the angle, well, if you give them as no, I am making a mistake. If you give them as vector, you have totally defined them, because vector has both magnitude and direction. So, there is no confusion if you are giving them as vectors. But sometimes we want to play with the scalars. So, instead of giving the vectors, we want to give the magnitudes of the vector. So, instead of giving vector A, we give the magnitude A, magnitude B and magnitude C. So, if we give only the magnitude, these 3 magnitudes, then the shape is not fully defined, because the angles between these magnitudes can be different. So, we need to give angle also, and the notation or convention is that alpha is the angle between B and C. So, see A, B, C and alpha, beta, gamma. So, B and C we leave A. So, whatever we are leaving, we are converting that into the Greek sequence. So, B angle between B and C, A is left out, alpha. Angle between A and B, C is left out, gamma. Angle between A and C, B is left out, beta. So, that convention is used. So, instead of 3 vectors, if you give these 6 numbers, then also you have defined the unit cell size and shape. So, this is what is called. So, A, B, C will be called the basis vectors, A, B, C as the basis vectors, whereas the length and the interaxial angle, those 6 numbers are called the lattice parameters. So, let us look at some lattice and non lattice translations here. So, is P q a lattice translation. This is a sodium chloride unit cell. Yeah, it is written here, sodium chloride unit cell. So, you can assume these to be chlorine and these to be sodium. So, is PQ a lattice translation? No. Why not? Takes me from a chlorine to a sodium. So, it does not take me to an equivalent site. Equivalence require that I go from chlorine to chlorine. So, twice this vector will be a lattice translation, but this vector is not a lattice translation. A to B, yes, this is not, this is yes. C to D, yes. You have to look little carefully. It may not always be that if chemically same atoms or ions are being connected, that has to be a lattice vector. We will see examples. Sometimes chemically same elements also may be locally in different configurations. So, they may not be forming an identical site. I think yesterday I tried to give you a 2D example, if I remember, that we have chemically identical atoms, sorry, even 1D, not even 2D, 1D example. So, if in 1D we are going like this. So, all are same element, but if I go from here to here, that is not a lattice translation, because these two are not equivalent atoms, they have different neighborhood. How they have different neighborhood? Both have one neighbor each at the same distance. So, they have different neighborhood, because if I go towards the left, if I right, if I go towards the right, if I go in the positive x direction, I find a neighbor for 1, but if I do the same thing for 2, go in the positive x direction in by the same distance, I end up somewhere where there is nothing. So, 1 and 2 do not have identical neighborhood. 1 has a neighbor on its right, 2 has a neighbor on its left. So, this right left inversion also is noticed when defining the translational equivalence. So, C to D is also a lattice translation. In this case, you can verify a little bit more carefully. We also saw yesterday graphene. This is a nice 2D example, and if we select any particular carbon atom as my origin and then start thinking what is the lattice, how do I extract lattice of this graphene structure, then I think this is carbon and this is carbon. So, I can make a lattice like this, but then I find that then this will be defined as a lattice translation, and this atom also should have a neighbor displaced by the same vector, but that is not true, that is not true. So, this does not become this equivalent as a lattice point. But if I now look at this, if I now look at this has exactly the same environment. So, this has a neighbor here, this also has a neighbor here, this has a neighbor vertically up, this has a neighbor vertically up, this is a neighbor here, this is a neighbor here, and not only local neighbors, far off neighbors should also be the same. So, this has a neighbor there, this has also neighbor there by the same vector. So, in the entire pattern you have to look at the entire pattern. Usually we do not look at the entire pattern and we look locally because the periodicity guarantees, but means one has to be clear about that thing in mind, that its repetition or equivalence with respect to the entire pattern and not only with the near neighbor or nearest neighbor or so. Now, this the basis ABC gives you a what is called a crystallographic coordinate system, very important concept. Important simply because it is not and that is why the name crystallographic is being used, that it need not necessarily be Cartesian coordinate system with which we are familiar. and that is the major confusion which happens in doing crystallographic calculation or this transition. So, in crystallographic thinking, our unit cell, our ABC and alpha, beta, gamma defines my coordinate system. I am no more Cartesian. This is, so, along A is my x axis, along B is my y axis. So, the angle between x and y axis is gamma, whatever that gamma is, 120 degree for hexagonal crystals. Fine, I will live with that. I will not insist that the angle be 90 degree. And similarly, whatever the lengths A and B be, in Cartesian we say all are unit vectors, all are equal and all are unit. Here neither we are saying that they are equal nor they are unit, whatever A is 1.3 angstrom, B is 2.5 angstrom, C is 4.393 angstrom, fine, I will live with that. So, that is what is a crystallographic coordinate system, because why crystallographic means why take such a crazy coordinate system as against the nice, beautiful, well established and completely familiar Cartesian coordinate system, because you will quickly see that actually Cartesian will not give you such nice coordinates for what we are interested in, and that is the lattice points, as the crystal coordinate system will give, because we have selected A, B and C to be lattice translation. So, if I go from here, let us say, so origin obviously has the coordinate 0, and then there is a lattice point, at A, because A is a lattice translation. So, it should take me from a lattice point at the origin to another lattice point at A. So, this is also a lattice point. What is its coordinate? A 0 0. And what will be the coordinate of B? 0 B 0. Here itself you are seeing the beauty of the crystallographic coordinate system. Then there is something called fractional coordinate. Fractional coordinates. To simplify it further, we say that why call it A 0 0? Divide the first coordinate by A. So, A by A 0 0, which becomes 1 0 0. So, call this point 1 0 0. So, 1 0 0 is the fractional coordinate. So, suppose A was 2 angstrom, then A 0 0 was 2 angstrom 0 0, but I will call it 1 0 0. So, 2 angstrom is lost, 2 angstrom is lost, but that I am supplying separately by saying that I know what is the lattice constant. I have kept that data separately and secretly, that I know my ABC. So, even if you call it 1 0 0, I know that it is actually A 0 0 1 times A. So, this will also become 0 1 0, I know that 1 is in the second place. So, 1 time B, and this will become 0 0 1. So, I will say it is 1 times C, because 1 is in the third place. So, fractional coordinate is coordinate divided by the corresponding lattice parameter. Is equal to fractional coordinate. So, idea of fractional coordinate is fine. Another beauty of fractional coordinate, suppose I have something at the center of this face, face center. We have face centered lattices. So, suppose there is a lattice point at the face center also. What will be its coordinates? Half of 0. Suppose I change the angle gamma to gamma by 2. What will be the coordinate of the face center? Still half of 0. So, half of 0 blindly I know is the center of the bottom face of the unit cell. You do not have to tell me A, B, C, alpha, beta, gamma. So, that information is quickly transmitted. How hard will I have to work if you did not give me this fractional coordinate and gave it in terms of A, B, C, and even worse gave it a Cartesian system where the crystal was, let us say, triclinic. Similarly, the body center will become half irrespective of the unit cell shape. Do not think that half is the body center of cubic unit cell, but what will happen in the triclinic unit cell? Oh, the angles are some 39.6 and 122.9. So, I have to calculate the coordinates in the body center. No, crystallographers have made your life simple. Irrespective of the unit cell shape, the body center has to be half. So, that is the crystal coordinate system for you. Very nice system developed by crystallographers.